డాడీ వచ్చాడు. పాలు వేడి చేయమని వచ్చి చేయలేదు. వచ్చి పాలు ఫిల్టర్ చేయండి చేసి. Okay, I will start the session. Steady state analysis. I will start the steady state analysis of resistor, and I will discuss steady state analysis of resistor, inductor, and capacitor, and I will conclude. And later on, during afternoon session, I will start this steady state analysis of the combination of series parallel combination of this resistor, inductor, and capacitor. So let's start with the steady state analysis of this resistor. So you can see in this circuit, a pure resistor. Resistor is connected. Resistor is connected across an AC source. E is equal to what? Em sin omega t. When source is connected to the resistor, current of I small I amperes is flows through this resistor. Okay. Now current flows through this resistor. What will happen? There will be a voltage drop across the resistor. Okay. So property of the resistor is to oppose the flow of current. So there will be a voltage drop across the resistor. Let us assume the voltage across the resistor is VR or ER. So here I have given notation for voltage as E. I have considered the notation for voltage as E. So instead of writing V, I can even write ER or VR, or which you can represent voltage in terms of E or V. Okay. So now let us consider the given source voltage, instantaneous value of the source voltage, that is E is equal to what? Em sin omega t. Okay, E equal to Em sin omega t. So what is instant value of current? I equal to E by R. Resistance R value, isn't it? So I is equal to what? E by R. So E is nothing but Em sin omega t. Substitute Em sin omega t here. Okay, so I is equal to Em sin omega t by R. So you can replace Em by R with some notation Im. So Im is the maximum value of current. So I is equal to Im sin omega t. Okay, I is equal to Im sin omega t. So if you see here, if you compare the equations of E, voltage, instantaneous voltage, instantaneous value of current. So E is equal to Em sin omega t. I is equal to Im sin omega. So there is no phase angle difference between both the currents. Both are in phase. Okay. So phasor diagram, if you draw for this circuit, phasor diagram is this. So I might have written small letters. It's okay. So E is equal to I into R. Okay. You can write even small letters. I can write small e is equal to small I into capital R. Instead of writing here in this diagram, it is. So instead of writing that, I can write small e is equal to small I into capital R. Okay, and this voltage is in phase with current. So this is small I. So I and E are in phase with each other. They are overlapping each other. Okay. So voltage and current waveform, if you plot, both are in phase, so both will reach their minimum value and maximum values at same time. Okay, in phase means both will reach their minimum value and maximum value. Both will reach 0 and maximum at the same time. So if you see, this is current waveform, this is voltage waveform. This is current and this is voltage. Both are in phase with each other. So this is our power, instantaneous power waveform. Where the dotted line is nothing but instantaneous power waveform for the given resistive circuit. Okay, so now let us see the uh, steady state analysis of inductive circuit. Okay, only inductor is present in the given circuit. So if only inductor is present in the given circuit, so you can see here AC supply is given to this inductor. Okay, AC supply is connected to this inductor. AC supply voltage, instantaneous voltage E is equal to Em sin omega t, and because of this source, what is happening? Some I amperes of current flows through the inductor. So the voltage across the inductor, let us assume I'm habituated to write V. Voltage across the inductor, you can assume EL. Okay, so EL you can write. I couldn't write EL properly. Okay, so when an alternating voltage, AC voltage is applied to an inductive circuit, okay, what will happen is, in the, what to say, some EMF is induced, voltage is induced across the inductive coil. So that voltage that is induced across the inductive coil, across the inductor, that is known as back EMF. Okay, so there will not be any voltage drop here, okay, across the inductor, but the voltage that is appeared, voltage buildup, okay, across the inductor is known as back EMF or self-induced EMF. This induced EMF will oppose the cause producing it. Okay, it will be always opposite to the source. What is it? A source voltage. So when current flows through the inductor, what will happen? Magnetic flux lines are induced across the inductor. So here you can see this is inductive coil. Okay, this is inductive coil, and these blue color lines which are shown here, they are the magnetic flux lines. Okay, so when current is flowing through this coil, okay, this purple line is nothing but arrow mark is represents current flow. So this blue line represents the magnetic flux that is induced in the coil. So when current flows through the coil, what will happen? Magnetic flux lines are induced. Okay, so if current is gradually increasing, here it is written increasing, then the magnetic flux lines will also increase, and induced EMF is induced, voltage is induced across the terminals of the or across the coil, I can say. Okay, so the induced EMF, according to Lenz law, according to Mr. Lenz, the induced EMF will always oppose the cause producing. Its direction will be opposite to the direction in which supply is given. Okay, so now what is our applied voltage or supply voltage? That is E is equal to Em sin omega t. So voltage that is induced across the inductor, let us assume that is, I have written same notation. Okay, even if I write same notation, it's okay. The voltage that is induced across the inductor, I can write EL. Okay, it's better if I write EL. It would be more specific that it is the voltage across the inductor. EL equal to L into di by dt. Okay, so, and you can just rearrange the terms. You will get simply what I have done is I have sent L this side, so EL by L, and I have sent dt this side. So what is left over here? If you send L and dt to the other side, di will be left over. Di is equal to 1 by L EL dt. Di is equal to 1 by L EL dt. Okay, now we just integrate the above equation on both sides. If you integrate and if you simplify, okay, what you get is I is equal to Em by omega L sine. Actually you will get minus cos omega t minus cos omega t is nothing but sin omega t minus pi by 2. So I is equal to Em by omega L sin omega t minus pi by 2. You will get. Okay, simple mathematical simplification, nothing else. Okay, so now you know the applied voltage equation E equal to Em sin omega t, and current equation, what did you get? I is equal to Em by omega L sin omega t minus pi by 2. You can replace this I equal to Em by omega L by some notation Im. So I is equal to Im sin omega t minus pi by 2 is our expression. Now, if you compare these two expressions, I is equal to Im sin omega t minus pi by 2 with your first equation, that is the applied voltage equation E equal to Em sin omega t. If you compare those two equations, what you can observe, there is an additional term, that is minus pi by 2 in current equation. This minus pi by 2 is, okay, minus pi by 2 represents current lags voltage by some angle of pi by 2, that is in radians. In degrees it is 90 degrees. In degrees it is 90 degrees, in radians it is pi by 2. Now if you measure the impedance for the given circuit, impedance is what? Z is equal to E by I. Okay, so capital E means capital letters represent, what does they represent? RMS values. So you can write, instead of E you can write Em by root 2, instead of I you can write Im by root 2. Okay, what is the phase angle of E? There is no phase angle for voltage equation, isn't it? So that is 0. In your current equation there was a phase angle. What was it? Pi by minus pi by 2. Okay, so Em by root 2 at an angle of 0 degrees, Im by root at an angle of minus pi by 2. So root 2 cancel, you will get Z equal to Em by Im at an angle of pi by 2. Okay, so Em by Im, you can replace it with omega L. Okay, so why you can replace it with omega L? Why? Because see here, I equal to Em by omega L. Okay, so sorry, yeah, Im equal to Em by omega L. Here Em by omega L we have replaced with Im, isn't it? So instead of Im you can write Em by omega L. See here I can write Em by omega L. If I write Em by omega L, Em cancel. So you can send this omega L to the numerator. So Z is equal to omega L at an angle of pi by 2. So instead of omega L, you can write XL. So Z is equal to XL at an angle of pi by 2 for purely resistive, purely inductive, so not resistive, inductive circuit. The impedance will be equal to XL at an angle of pi by 2, where XL is the inductive reactance and its units are ohms. Okay, units for XL are ohms. Okay, so now if you draw the phasor diagram, here current lags voltage by an angle of 90 degree. So if you see here, yeah, if this is my voltage waveform, if you draw the waveforms, if you see, this is my voltage waveform. So when voltage is maximum, current is minimum. When voltage is minimum, current is maximum. But voltage reaches its maximum value before current reaches its maximum value. Therefore, current is lagging voltage here by an angle of how much? 90 degree. Okay, so this is voltage waveform. This is current waveform. Okay, so this is a phasor diagram of purely inductive circuit. Voltage is leading current by an angle of 90 degree. If anyone have any doubts, you can mention in the chat box. If I see the chat box, I will definitely reply. Okay, so this is it. Now let us see the average power for this inductive circuit. So average power is calculated for one complete cycle. So 1 complete cycle means 0 to 2 pi. So 1 by 2 pi integral of 0 to 2 pi EI E into I. Okay, voltage into current EI d omega t. Okay, I am writing in terms of radians. That's why. So what is E? E means Em sin omega t. I means Im sin omega t minus pi by t. Okay, so substitute E and substitute I and just simplify it and integrate it. You will get average value as C. Okay, simply substituting the voltage equation and current equation in the average power formula, and you will get average power equal to 0. So we can say that power consumed in a purely inductive circuit is 0 for one complete cycle. Okay, and okay, that's it. Now let us go to the steady state analysis of capacitive circuit. So here only capacitor is connected. Voice is not audible. Let me check. My voice is not audible. No, voice is audible because I have already told you. I am also one of the what to say viewer. I like you people. So in my another device, I am able to hear my voice. Just now I raised my voice and I tried to listen to it. My voice is audible. Please check your device. If there is any issue with your device from which you are attending this session. Okay, steady state analysis of capacitance. Let us see. So now, so let us apply voltage source, AC voltage source across the capacitor. And we already know when source supply is given to the capacitor, what will happen? Electric field is developed across the capacitor plates. Immediately, no current will flow through the capacitor plates. Okay. When electric field, not immediately, sorry. Initially, voltage developed is 0, not current. Current is not 0. Initially, voltage developed across the capacitor plates is 0. And when voltage is developed across the capacitor plates, that is electric field is developed across the capacitor plates, current will not flow through the capacitor. Okay. So whenever AC voltage is applied across the capacitor plates, then what will happen is this the current will start to flow through the capacitor. Capacitor starts to charge. Okay, and if source is disconnected, capacitor will start to discharge. Okay, and we already know capacitor consists of two plates and they are separated by an dielectric medium. Okay, now what is our voltage here? Supply voltage is V equal to Vm sin omega t. So consider that expression V equal to Vm sin omega t. Now when supply is given, what will happen to the capacitor? Capacitor starts to charge. So let us assume Q is the charge that is given by C into V. Formula for Q is what? The charge across the capacitor. You can calculate the charge across the capacitor by this equation Q equal to C into V. Okay, now what is the current that is flowing in the circuit? To charge the capacitor, I is equal to dq by dt. Okay, formula for current in a capacitor circuit, I is equal to dq by dt. Okay, what is Q? Q is equal to C into V. What is V? V equal to Vm sin omega t. So substitute all these in this equation of current and you just simplify it. C and Vm are constant, bring them aside. D by dt of sin omega t is nothing but cos omega t. Okay, omega into cos omega t, not simply cos omega t, omega into cos omega. So I is equal to what? Omega CVM cos omega t. That's what you will get. Now cos omega t, um, you can rewrite it as sin omega t plus pi by 2. Okay, you can replace it with sin omega t plus pi by 2. Cos omega t can be rewritten like that. And here omega c was multiplied with Vm, so you just have rewritten it in terms of 1 by omega c. So 1 by omega c is nothing but xc. You can replace it with some notation xc. So Vm by xc you will get. So I is equal to Vm by xc sin omega t plus pi by 2. So where xc is equal to 1 by omega c. Okay. So Vm by xc can further be replaced by some single notation Im. So Im is nothing but what? Vm by xc. So I is equal to Im sin omega t plus pi by 2. So in a pure capacitive circuit, the current will flow through the capacitor. Current flowing through the capacitor, what will happen? It will lead the voltage by an angle of 90 degrees. So so here you can see plus pi by 2 you have one. Okay. If you compare the current and voltage equations, current equation if you see, I is equal to Im sin omega t plus pi by 2. What is voltage equation? V is equal to Vm sin omega t. Okay. So current is leading voltage by an angle of 90 degrees. So if you draw the, if you compare, if you can draw the phasor diagrams, and if you draw the voltage and current waveform, you can see here uh, when voltage is still 0, this is voltage. Blue line is voltage. Blue wave is voltage wave, and purple wave is current wave. So when voltage is still 0, current has already reached to its maximum value. Okay, so which is leading initially. Okay, just consider the initial condition. So which is leading? Current is leading voltage by an angle of 90 degrees here. So for purely capacitive circuit, current leads voltage by an angle of 90 degrees. So if you draw the phasor diagram, you can see here, this is my cursor, yeah. This is voltage and this is current. Current is leading voltage by an angle of 90 degrees. Okay. Now let us calculate the instantaneous power for this circuit. So we know P is equal to instantaneous power is what? P equal to V into I. What is V? Vm sin omega t. What is I? Im sin omega t plus pi by 2. So Vm, Im are constant. Just bring them aside. If you bring them aside, what is left over? Sin omega t into sin omega t plus pi by 2. Sin omega t plus pi by 2, you can replace it with cos omega t. Okay. So you just multiply and divide with 2 to this expression. I have skipped one step here. Just multiply and divide by 2 and 2 sin omega t cos omega t is number sin 2 omega. Okay, so P is equal to what? For the purely capacitive circuit, instantaneous power is Vm Im by 2 sin 2 omega t. So if we determine the average value for one complete cycle for this capacitive circuit, average power is P average is equal to 1 by 2 pi for one complete cycle, integral of 0 to 2 pi P d omega t. So P, just now we have got some expression, you substitute that expression, you just simplify it, you will get P is equal to 0. Okay, the power consumed in a purely capacitive circuit is what? 0. So the capacitor will receive energy during the first quarter of the voltage and return the same during the next quarter of the voltage. Okay. So I can discuss this. That's it. I wanted to discuss only series, only R L&C, but still hardly 1 hour is over. Possible I can discuss this steady state analysis of series RL circuit. Let us see. Steady state analysis of series RL circuit, RL, RC and R L&C also. Let me complete. Okay. will be good if I complete that. So steady state analysis of RL circuit. Okay, so RL means here I have considered series RL circuit. R and L are connected in series. Now here I have considered what to say a resistor and inductor, both are connected in series. Source voltage is V equal to Vm sin omega t, and voltage across the resistor, let us assume VR, voltage across the inductor, let us assume VL, current through the whole circuit is I. Okay, so what is the voltage across the resistor? VR equal to R into I. What is the voltage across the inductor? Voltage across the inductor is what? VL equal to XL I. Voltage across the inductor is VL equal to XLI. Okay, so I can even write this I as small I. Here in this circuit I have considered small I. You can write small I. Okay, so I have not written there small I, but I might have written. Now you can draw the phasor diagram for this. If you draw the phasor diagram, we already know. I will just roughly draw it here. We already know that what to say, the VR is in phase with voltage across resistive voltage is in phase with current. So VR is in phase with current I. Okay, VR is in phase with current I, and for inductive circuit, current lags inductive voltage VL by an angle of 90 degree, isn't it? So current lags voltage by an angle of 90 degree for inductive circuit, and current will be in phase with the capacitive, resistive circuit. So this is it. Now just join the VL, draw a dotted line from VL, draw a dotted line from VR. They will meet at certain point. From the origin, draw a straight line to this point. Okay, that is nothing but V. So V is the vector sum of VR and VL. So angle made by V and I. Angle between V and I is some phi. Angle between V and I is some phi. Phase angle between voltage and current. Okay. Phase angle between voltage and current is V and I. Okay, so this phi, if you see, phi is not exactly 90 degree for inductive circuit. What did I say? Voltage will lead current by an angle of 90 degree. But here, since resistor is also there, voltage will not lead current by an angle of 90 degree. Voltage will lead by some angle phi. So the phase angle between voltage and current is in between 0 and 90 degree. So what is V? V is the vector sum. This V is the vector sum of VR and VL. So you can represent V is what? V is equal to VR plus VL. VR is nothing but R into I. VL is nothing but I into XL. Okay. So vector sum. So here itself you can write J. I didn't write. So JXL I. So V is equal to R plus JXL I. So send this I to the other side. V by I is equal to R plus JXL. V by I is nothing but Z. So Z is equal to R plus JXL. So if you write the expression for impedance, Z is equal to vector of Z is magnitude at some angle phi. So what is the vector form of Z? R plus JXL. R plus JXL can be written as Z square is equal to R square plus XL square, or Z is equal to root of R square plus XL square. XL is nothing but omega L, so you can replace XL with omega square L square. Now what is phi? Phi is the phase angle between the, if you draw the impedance triangle, you can draw the impedance triangle. Okay, so if this is phi, and we already know R is the real part and XL is the imaginary part. So I can draw R here. This is the impedance triangle. This is XL and this is Z. So what is phi? Or from this impedance triangle I can write tan phi, isn't it? I can write tan phi from this impedance triangle. What is tan phi? XL by R. XL by R. So what is phi? Phi is equal to tan inverse of XL by R. Okay, phi is equal to what? Tan inverse of XL by R. So you can determine the phase angle between voltage and current simply by impedance triangle. So phi equal to tan inverse of XL by XL is nothing but what? Omega L. XL is nothing but omega L. So XL is omega. So phi equal to tan inverse of omega L by R. Okay. So here what to say the current. Okay, voltage equation is what? V equal to Vm sin omega t, and in inductive circuit, as I have already told you that current will lag voltage by an angle of phi. Therefore, I will be what? Im sin omega t minus phi. V is equal to Vm sin omega t. Since I is lagging voltage by an angle of phi, I can write I equal to Im sin omega t minus phi, where Im is nothing but Vm by Z. Okay, Im is nothing but Vm by Z, and pi equal to tan inverse of omega L by R. You can draw the voltage and current waveforms. Here, this is voltage waveform. Okay, current lags voltage by an angle of phi with some phase delay. Okay, you can draw current waveform. Okay, so with some phase angle displacement, this from this instant current waveform will start. Now, if you want, you can even write the instantaneous power for this RL circuit. So P is equal to V into I. What is V? Vm sin omega t. What is I? Im sin omega t minus phi. So you just simplify it. Okay, if you simplify, you will get P is equal to instant power equal to Vm Im by 2 cos phi. Vm Im by 2 cos 2 omega t minus phi you will get. Okay, so once again, if you observe this second term, this is first term, this is second term. So in the second term, if you see, there is a double frequency term. So if you determine the average value for the double frequency term, the average value for one complete cycle, that is from 0 to 2 pi, it will become equal to 0. So for one complete cycle, what is our instantaneous power or average power? Second term is becoming 0. So average power is equal to Vm Im by 2 cos phi. 2 can be written as root 2 into root 2. So Vm by root 2, Im by root 2. Vm by root 2 is V, Im by root 2 is I. So capital V and capital I are what? They are the RMS values. So average power is VA cos phi for RL circuit. Okay. And what about the power factor? Cos phi is nothing but the power factor, isn't it? Cos phi is nothing but the power factor. You can draw voltage triangle, impedance triangle, or power triangle for this RL circuit. So I have already shown you. I think you already know voltage triangle and what to say, power triangle. If you know the phasor diagram, you can easily draw the triangles. If you see here, and this is VR, this is V, this is VL. This line is parallel to this line. So just draw a straight line here, write VL. Okay, so this is nothing but voltage triangle. This is our voltage triangle. So you can draw the voltage triangles. Okay, and from the voltage triangle, you can write down the power factor equations. Okay, so from the voltage triangle, power factor is So this is VR. I'm unable to draw it. So I will simply draw like this. This is triangle. Okay, so this is VR. This is VL. This is V. So what is cos phi? Cos phi is nothing but VR by V. Similarly, impedance triangle. If I draw the impedance triangle, this is my impedance triangle. This is R. This is XL. This is Z. And this is phi. From the impedance triangle, what is power factor? Cos phi is what? Cos phi is Z by R. Okay, similarly power triangle. So draw the power triangle. This is phi, angle is phi. Okay, angle is phi. So active power P, reactive power Q, apparent power S. So what is the power factor cos phi from this triangle? Cos phi is equal to here, I think base by hypotenuse, isn't it? Base by hypotenuse. Cos phi is base by hypotenuse, P by S. Okay. Cos phi is equal to P by S. Okay, cos phi is equal to P by S. Okay, so base by hypotenuse. That's it, P by S. That's it. So these are all the power factor equations for the RL circuit. If anyone have any doubt, you just mention in the chat box. I will discuss about it. Now let us see the steady state analysis of RC circuit. So you can see here a resistor and a capacitor, they are connected in series across an AC voltage source. Okay, resistor and capacitor are connected in series across an AC voltage source. So voltage across the resistor, let us assume, is VR, and voltage across the capacitor is VC. Source voltage V equal to Vm sin omega and current is I. Okay, now what is the VR? VR is nothing but R into I. You can write small I. Here I have mentioned I, small I. And what is the voltage across the capacitor? VC is equal to XCI. Okay. So now, what is V? Source voltage V. V is the vector sum of VR and VC. V is the vector sum of VR and VC. Okay. Now, V is the vector sum of VR and VC. So you can draw the phasor diagram. See here. And you know capacitive current. Capacitive current will lead voltage by a 90-degree angle. So, and if this is current, and what is the resistive voltage? It will be in phase with the current VR. And what are the capacitive voltage? It will lag current VC. VC will lag current by an angle of 90 degree. And draw a dotted line from this VC, tip of VC and tip of VR. Draw a dotted line. From the origin, draw a straight line. What is this? This is nothing but V. So angle between I and V is, let us assume it is phi. Okay. So this is the phasor diagram of RC circuit. Here, the angle between voltage and current, that is V and I. This is V, this is I. Current will be always less than 90 degree. So this part you can say, this part you can call it as voltage triangle. Okay. Now let us consider the vector equation. V equal to what? VR plus VC. VR is nothing but I into R, and VC is nothing but J XC into I. So why did we write minus here? Okay. Why did we write minus? You can even write plus. So usually if you have an RLC circuit, in an RL and C circuit, usually XL will be greater than XC. Okay, if XL is greater than XC, then okay, if it is greater than XC, XL is considered as positive, XC is considered as negative. Okay. Now if XC is greater than XL, then XC is positive and XL is negative. So usually what happens is inductive reactance will be greater than the capacitive reactance. That's why you will consider minus here. So minus J XC I. So R minus J XC into I, and V by I is nothing but impedance. So vector of impedance is magnitude and phase angle. Minus 5 we have considered. Why did we consider minus 5? Why? Because usually capacitive reactance will be less than inductive reactance in a given circuit. Of course, here we didn't consider any inductor. We have considered only RC circuit, but usually that's the case. That's why we will write minus here. So magnitude of Z is nothing but root of R square plus XC square. So XC is nothing but 1 by omega C. Just substitute that. And phi equal to tan inverse of XC by R. Why tan inverse of XC by R? From the impedance triangle. From the impedance triangle, this is if this is R, and if this is XC, and this is phi, then this is Z. Then what is phase angle? Cos phi, or simply tan phi, not cos phi. Here we are not determining the power factor, isn't it? Simply tan phi is nothing but what? Opposite by base. So tan phi. So tan phi is equal to what? XC by R. Tan phi equal to XC by R. So phi equal to tan inverse of XC by R. Okay, so if you simplify, you will get phi equal to tan inverse, and instead of XC, replace it with 1 by omega C. You will get tan inverse of 1 by omega R C. Okay. So now what is current what is our voltage equation? V equal to Vm sin omega t. So here current is leading voltage by some angle phi. Okay, it is leading voltage by some angle phi. So you can write current equation I equal to Im sin omega t plus phi. Okay, where Im is nothing but Vm by Z. Okay, and what about phi? Phi is tan inverse of XC by R, or phi equal to tan inverse of 1 by omega RC. Now if you draw the voltage and current waveform, current is leading voltage by an angle of phi. So see here, this is my current waveform. With some phase delay, voltage waveform starts. So this is the voltage and current waveform for RC circuit. And you can, similar to your RL circuit, you can determine the power factor. Power factor formula is cos phi, power factor for voltage triangle. So you once again draw the voltage triangle. Okay, so this is VR, this is VC, VC, and this is V. So what about cos phi? That is phi. This is phi. Okay, so this is phi. So what is cos phi? Base by hypotenuse, VR by V. So power factor from voltage triangle. Similarly, Power factor from impedance triangle. Impedance triangle, this is R, this is XC, this is Z, this is angle phi. This is angle phi. So what is cos phi? Base by hypotenuse R by Z. Okay, power factor from impedance triangle. Similarly, next power triangle. This is phi. Sorry. Base angle phi. Okay. This is real power and this is reactive power. This is apparent power. So what is power factor from the power triangle? Sorry, this is P. I have written R. Real power P. Okay. So P by S is the power factor from the power triangle. Okay, I have summarized all these in a tabular column. Okay. Now let us see series RLC circuit. So in this series RLC circuit, resistor, inductor and capacitor are connected in series. Source voltage is V equal to Vm sin omega, current is I. So voltage across the resistor, inductor and capacitor. VR is the voltage across the resistor, VL equal to voltage across the inductor, and VC, let us assume, is the voltage across the capacitor. Now you can write down the voltage equations of resistor, capacitor, and inductor. Voltage equation of resistor is VR is equal to R into I. Inductor is VL equal to XLI. Across the capacitor, VC is equal to XCI. Okay. Now we already know VR, that is voltage across the resistor, is in phase with the current I. Voltage across the inductor, it will lead the current by an angle of 90 degree if it is a purely inductive circuit, and we know that if it is a purely capacitive circuit, current will lead the voltage by an angle of 90 degree. Okay. So what is the total vector sum of all these voltages? Is my cursor. V is equal to what? Vector sum of VR plus VL plus VC. V is equal to VR plus VL plus VC. Okay. So and as I have already told you in the previous session that phasor diagram, sorry, not phasor diagram. I have told you that usually XL will be greater than XC. Okay. So if you draw the phasor diagram, we will assume that, okay, we will assume that XL is greater than XC, means we will assume XL is positive, okay, and XC is negative, or VL positive and VC negative. So see here, this is VR, okay, that is in phase with I. VL leads current by an angle of 90 degree. VC lags current by an angle of 90 degree. Okay. So let us assume XL is greater than XC. When XL is greater than XC, you can consider VL, you can rewrite or rearrange the terms if you are determining the impedance as Z is equal to R plus J XL minus XC. You can rewrite like that. Similarly, instead of considering the negative section, negative part means negative axis on the imaginary where VC is there, we will just shift this VC to the opposite side. If it's shifted to the opposite side, it will become negative. Of course, it is on the negative side. Okay, so since XL is greater than XC, I'm considering the axis, imaginary axis on which VL is there. Okay, and since XL is greater than XC, so you must write XL minus XC. So instead of writing that in terms of voltage, if you write, you write VL minus VC. So this is VL minus VC. This is VR. So what is the vector sum? Is V. Okay. So you can shift this VL minus VC to this other side. So you will get the voltage triangle. This is my voltage triangle. This is VR. This is VL minus VC, and this is V. Okay. So if this whole phasor diagram might have changed if XC was greater than XL. If XC was greater than XL, so then I might have written VC minus VL. VC minus VL okay, here VR is there, so draw a dotted line. From here, draw a dotted line. From here, drawing this. This is V. Okay, so this might not have been there. This might not have been there. So this is the phasor diagram for XC greater than XL. Okay. So usually inductive reactance will be greater than capacitive reactance. That's why this is a phasor diagram. Okay, and this is the voltage triangle. This is the voltage triangle. Okay. So in the next slide, see here I have even drawn that. I didn't see. See. XC timing is not being selected. XC greater than XL. So this is my phasor diagram. What? XC greater than XL. VC minus VL. Okay. Now let us see the voltage equation. What is voltage equation? V is what? Vector sum of VR plus VL plus VC. What is VR? R into I. VL is JXLI. VC is minus XCI. So here I have considered which case? I have considered XL greater than XC case. Okay, I have considered this phasor diagram. XL greater than XC. That's why I have written minus JXC. So here take I common, you will get V is equal to R plus JXL minus XCI. Send I to the other side, you will get Z. Z is what? Vector of Z is magnitude at an angle. Magnitude with its angle is nothing but vector 1. So Z is nothing but root of R square plus XL minus XC whole square. So Z is nothing but Z is equal to R plus Z is equal to R plus J XL minus CC. Okay, so R plus J XL minus XC. So R plus J XL minus XC, you can write it as Z square plus R square plus XL minus XC square. Okay. So what is phi? From the impedance triangle. Draw the impedance triangle. This is Z. This sorry, not Z, that is R. I will erase all rings and I will answer in the x-axis, real axis is R. This is XL minus XC. And this is Z. So Z is equal to root of R square plus XL minus XC square. So what about phi? Phase angle. So you can tan phi is what? Opposite by base. Opposite was XL minus XC by R. So tan phi is equal to XL minus XC by R. Phi equal to tan inverse of XL minus XC by R. Okay. So I is equal to Im sin omega t plus or minus phi. Plus in the case of capacitive circuit, minus in the case of inductive circuit. Okay. So here if both a capacitor and inductor are there, you will consider minus. If XL is greater than XC, you will consider plus if XC is greater than XL. Okay. If XC is greater than XL, you will consider plus. Otherwise, it is minus. Okay. And you can even draw the voltage and current waveforms. If XL is greater than XC, voltage leads current. Okay. If XL is greater than XC and XL greater than XC, then voltage is leading. If you see voltage waveform and current waveform, voltage leads current by an angle of phi. If XC is greater than XL, current is leading, voltage is lagging. Okay, and you can even write the power equations. So average power P is equal to VA cos phi. Okay, that is I square R, and reactive power is Q is equal to average power is nothing but active power. Q is equal to VI sin phi I square X, and apparent power is given by S is equal to V into I, that is I square Z. Similarly, you can draw the power triangles. When XL is greater than XC, this is the power triangle. Okay, and when XC is greater than XL, okay, this is the power triangle. Okay, so means Q will be in the positive imaginary axis for XL greater than XC. Q will be in the negative imaginary axis. You just see the arrow marks. Q is in the negative imaginary axis when XC is greater than XL. That is it. Okay. Now we can even determine the power factor for what is it? You can even determine the power factor PF is equal to what? Cos phi. So I will write that PF. So PF power factor is cos phi. So from the voltage triangle, I am not going to draw the voltage triangle, impedance triangle, and power triangle. Already I have drawn in the previous cases. And from the voltage triangle, impedance triangle, and the power triangle, you will get the power factors. Okay, so I hope you might be able to draw from there. Draw the power factors. Okay, so now let us see the parallel circuits. We have seen series. Now let us see the parallel circuits. So, I didn't make any, what to say. So parallel means resistor, inductor, capacitor will be connected in parallel. So let us start with parallel RC circuit. Okay, let us start with parallel RC circuit. So this is our parallel RC circuit. So here you can see there is a AC voltage source. Across it, a resistor and capacitor are connected in parallel. Since they are connected in parallel, what will happen? The current that is flowing into the circuit from the source, it will divide into two branches. Okay, so current flowing through the resistor is IR, current flowing through the capacitor is IC. Okay, so what is capacitance? XC is equal to 1 by omega C. Omega is nothing but 2 pi L. Okay, now since these capacitor resistor are connected parallel to the voltage source, voltage across the source will be same as voltage across the resistor and same as voltage across the capacitor. So when elements are connected in parallel, their voltages will be same. So V is equal to VR, VR equal to VC. So now what is the current in the resistive branch? Current in the resistive branch, current I is equal to V by R. V is what? V. Source voltage is V and resistance is R. So IR is equal to what? V by R. IR is equal to V by R. Similarly, what is the current in the capacitive circuit? IC is equal to V by XC. Okay. Similarly, as I have already told you from the diagram, the total current is what? IR plus JXC. So JXC, why? Because reactive components come into existence if capacitor is there. That's why. So I square is equal to R square, IR square plus IC square. So I is equal to IR means we know IR means V by R and IC means V by XC. So just substitute in the above equation and determine I. What about impedance? Z is equal to what? Z is equal to V by I. Z is equal to what? Simply V by I. Now you can draw the waveforms. This is our source voltage. Okay. With this source voltage, resistive current will be in phase. So see here, both are starting and ending at the same instant. Okay. Whereas capacitive current will lag voltage by some angle or lead voltage by some angle, isn't it? Capacitive current will lag or lead. What will happen? Capacitive current will not lag, it is leading. You see, when the voltage is still 0, current is maximum. Okay, so capacitive current will lead voltage by an angle of 90. So if you draw the phasor diagram, you see IR is in phase with V, whereas IC is leading voltage by an angle of 90 degree. Now from IR draw a dotted line, from IC draw a dotted line, join it, consider this as some angle phi. Join it, that is nothing but I. I is the vector sum of IR plus IC. Now let us see the parallel RL circuit. Now we have seen, just now we have seen RC circuit. Now let us see parallel RL circuit. So here also, what to say? What is say? Vs, source Vs, here it is in this diagram I have written Vs. So Vs is equal to Vr is equal to Vl. Vs equal to Vr equal to Vl. And what about the current that is coming out of this source, total current? Here in this diagram it is written IT, that's why I am writing IT. IT is equal to what? I R plus I L, vector sum of IR and IL. Okay. What about IR? Is it there here anywhere? I have written. Okay, I have written it. So it is there. I already wrote it. I thought it's not there. That's why I was trying to write. So here Vs is equal to Vr equal to Vl. So what about IR? IR is nothing but Vs by R. Inductive current is XL equal to Vs by XL. So what about total current equal to IR plus, if I write, I earlier wrote in terms of vector, here I have replaced it with the J term here. So IT equal to IR plus JX IL. So IT square is equal to IR square plus IL square. So we know what is IR and IL. Just substitute it, you will get IT. Okay, so what is impedance for this circuit? Z is equal to V by I. So if you draw the waveforms, here for resistive current will be in phase with source voltage, whereas inductive current will lag voltage by some angle. See here, it is lagging, it is already negative. Okay, this is negative. So V and phasor diagram, V and IR are in phase, whereas IL is lagging V by an angle of, actually pure inductor will lag by an angle of 90. Draw a dotted line from IL, draw a dotted line from IR, and you will get I. So V and I are having phase angle difference of phi. I is lagging V by some angle phi. I lags V by some angle phi. Now let us see parallel RLC circuit. Parallel RLC circuit. So this is it. This is my source voltage. RLC are in parallel. So instead of this diagram, it's better if I draw the diagram like this. So I can say IS is dividing into IR plus IL plus IC. Okay. So all these three elements are connected in parallel. So IS is dividing into IR. So IS is equal to vector sum of IR, IL and IC. So we have considered all the three elements. So what about the resistive current? IR equal to Vs by R. Inductive current IL equal to Vs by XL. Capacitive current is IC is equal to V by XC. Okay. Now IS is nothing but what? IS is equal to IR plus J of XL minus XC. Why we are writing XL minus XC? Why? Because we are assuming XL is greater than inductive reactance is greater than capacitive reactance. So that you can rewrite as IS square is equal to IR square plus IL minus IC whole square. So IS is equal to root of equation of IR, equation of IL and equation of IC. Just replace all the I terms with their respective voltage and impedance and reactive values. You will get this IS equation. Now if you draw the phasor diagram, in the phasor diagram, this is my source voltage. IR is in phase with source voltage, and IL lags purely inductive current will lag voltage by an angle of 90, and IC will lead voltage by an angle of 90. Okay. Now I have assumed XL greater than XC, therefore I have written instead of this IC I have sent to the other imaginary side. So IL minus IC I have written. So draw a dotted line from here, draw a dotted line from here. This is nothing but IS. So IS will lag VS by an angle of phi. Okay, by an angle of phi. So what about the here, since elements are connected in parallel, instead of determining impedance, I am determining admittance. Admittance is reciprocal of impedance. Okay. Admittance is reciprocal of impedance. Z is equal to V by IS. So here I have written IS by V. So Z is equal to root of R square plus XL minus XC whole square. So instead of that, I have written Y equal to 1 by R square plus 1 by XL minus 1 by XC whole square. Okay, so I will discuss a numerical problem, one or two numerical problems, and I will conclude this session. So see here in this they have what did they have? They have asked us to draw a phasor diagram. Vector diagram means phasor diagram for the given figure. So they have mentioned some V1 voltage and V2 voltage. What is V1 voltage? V1 is the voltage across resistor and this inductor. It is the voltage across resistor, inductor and capacitor. Find the current. They have asked us to determine V1, V2, and they have also asked us to determine the power factor. Okay, they have also asked us to determine the power factor. So let us see. So in this diagram, source voltage is given 200 volts and frequency 50 hertz. Just go through this. I will come back. Okay, so let us solve this numerical problem. So if you observe here in this diagram, if you see, resistance values are given. Resistance is given, resistance in ohms is given. But here inductance value and capacitance values are given. So all the terms, whenever we want to simplify numerical problems, all the capacitive and inductive values must be replaced by their reactance values. Okay, so we have to determine the reactance of this inductor, reactance of this inductor, and reactance of this capacitor. Okay, so let us consider first inductor. Let us consider reactance is what? 2 pi fl. So f is given 50, 2 pi 50 into L value 0.05. Simplify it, you will get this value. Similarly, for another inductor, to substitute the formula, L value and 2 pi f formula, and 2 pi into f is 50 and L value 0.1, you will get XL value. Similarly, for capacitor, X is equal to 1 by 2 pi Fc. So 2 pi into F is 50, C is 50 microfarad. Yeah, it is 50 microfarad. So 50 into 10 to the power of minus 6. So you will get capacitive reactance. Now you see what you can see. All the values are in ohms. Okay, ohms and ohms. So since all the values are in ohms, you can easily you can simplify the given circuit. So first of all, what I am going to do is I will determine the impedance for the given circuit. So total impedance. So what is the total impedance for this given circuit? Okay, simply we have to add all the impedance, resistance values and reactance values. Okay, so see here. So Z is equal to this is resistance 10 ohms. Yeah, I will just copy this image there. So see here. So Z is equal to 10 ohms. Okay. So next it is inductor, inductance, inductive reactance. How much did we get? J 15.71 ohms. And another inductive reactance is 31.42 ohms. Whereas capacitive reactance, how much did we get? 63. So if you compare XL1 and XL2 with XC, XC is greater than XL1 and XL2. So we can say capacitive reactance, since XC is greater than XL, XL should be negative and XC should be positive. That's why if you see here, where is it? Yeah, if you see here, for this inductor, whatever reactance that I have got, I have written in terms of minus. Plus resistance 20. So 20 I have written. Next, inductive reactance, what did I get? 31.42 I have written in terms of minus. Why? Because it is less than capacitive reactance. Capacitive reactance is greater than XL1 and XL2. Therefore, I have written, consider it as positive. Okay. So instead of adding all the resistance values and reactance values, inductive reactances I have considered negative. Why? Because capacitive reactance was greater than inductive reactance. So if you are listening, you will be able to follow. So after simplification, I have got this. And using a scientific calculator, you can convert this rectangular term into polar term. I have converted rectangular into polar. Okay, now what is the current in the given circuit? I. All the elements are connected in series. So definitely I will be same. I is equal to V by Z. V is 200. Z just now I have calculated. I have considered only magnitude. So you can even consider the angle. It doesn't matter. Okay, so I is equal to 200 by 34.25. So you simplify, you'll get 5.84 amperes. So you can even consider angle. You can write 200 at an angle of 0 degrees divided by 34.25 at an angle of 28. And if you write the angles, I will write the angles. 0 degrees. If angle is not mentioned, you must consider 0. Okay. Here angle is what? Cursor, it just irritates me. .85 degrees. So, and if you are dividing magnitudes and if you are the angles are, if numerator angle and denominator angle is there, so then you must subtract. So you will get 5.84. 0 minus 28 means minus 28.85 degrees for current. Amperes. So my current is 5.84 at an angle of 28.85 degree amperes. Now they have asked us to determine V1. Okay, so okay, so I have considered here. I didn't in this equation, in the for the simplification that I have done earlier, I didn't consider the angle. I have considered only magnitudes here. That's why I didn't write angle here. You can consider angle and you can write minus 28.85 degrees. You can write it. I didn't write. If you want, you can write it. So now impedance is what? Simply 10 minus J 15.71. If you just convert into polar form, you will get this. Now V1 equal to Z1 I1. So you just write Z1 value and you can write I1 value. I1 angle you can write minus 28.85. You just write it and simplify it, you will get some other answer. Similarly, Z2 equal to what? Z2 is equal to resistance, inductive reactance and capacitive reactance, isn't it? Z2 is what? So in this diagram, Z1 is, this is Z1. From here to here. From here to here, it is Z. Okay, it is Z2. So determine Z2. Okay, determine Z2. I have got in rectangular form, convert that into polar form. After that, multiply Z2 with I, you will get V2. V2 equal to Z2 into I. Okay, instead of here I have considered 0, no need to write 0, actually it is, I didn't consider angle there, otherwise I might have written 28 point, it is minus 28.85. Okay, minus 28.85 degrees. Okay, now what about power factor? It is the cosine angle. Okay, so whatever current angle is there, angle of current, that angle you can write it down. So that is minus 28.85. So magnitude, right magnitude, and you will get the power factor is leading power factor. Of course, you have seen XC is greater than XL. So definitely power factor will be leading. And you can even draw the phasor diagram. Okay, you can draw the phasor, and this is I. And V1 is lagging I and V2 is leading I. How is it possible? You just see here. V1 lags I. V1 is lagging I. Why? Because it is having R and L. V2 is having R L C. Okay. Whereas XC is greater than I, XL. Therefore, definitely V2 is leading I and V1 is lagging I. So their phasor diagrams, phase angles. V1 phase angle according to this simplification, V2 is 58.19 and V1 is minus 57.52. So you just substitute that, you will get the phasor diagram. Now let us consider one more numerical problem. I will discuss this and I will conclude this session. So in this you can see current is given 25 at an angle of 90 degrees. They have asked us to determine I1 and I2. So where is I1? This is I1, this is I2. So now first of all let us determine the impedance of this line. And what is the impedance? K minus J4 ohms is the impedance. And what is the impedance in this line? Okay, it is, or this line or branch, it is 10 ohms. Impedance is 10 ohms. So here only resistor is there. So you may think that I must write only resistor is there. It is not the impedance, it is the resistance. In this branch, total impedance is equal to resistance. Okay, in this branch, total impedance is equal to resistance plus capacitive reactance. And if you observe here, he has mentioned capacitive reactance. He didn't give capacitance value minus 4J ohms. It is units are in ohms. If units across the capacitor or inductor in ohms, that means that it is the reactance value. Okay, so total current I is given. Okay. Now just simplify this. Current I have gone for current division rule. I know the total current I value. I know the impedance across each element. So I1 I have determined. So I have substituted I value. I have written Z2 divided by Z1 plus Z2. That is current division rule, and I have simplified. I have got I1. So I know I1. What can I determine? I2. I2 is simply, no need to go, once again, no need to go for current division rule. Simply I2 is equal to what? I minus I1. So what is I? This is 25 at an angle of 90. I1 I have got 18 in the above expression. 18.38 at an angle of 107.1. Just simplify it. You will get I2 current. Okay. So we have seen series circuit problem and we have seen parallel circuit problem. One more small problem with both series and parallel combination. So see here in this numerical problem, we have to determine the current in the given circuit. We have to find the power consumed and power factor. So see here series elements and parallel elements both are there. So, and if you observe here inductance value is given, here inductance value is given, here capacitance value is given. So they didn't give us reactance values. So determine the reactance for this inductor. So inductive reactance XL1 is 2 pi FL1. 2 pi F value is given, that is 50 hertz. So 50 into L1 is how much? 0.01. Just substitute, you will get XL1. Similarly, this term XL2 is 2 pi FL2. 2 pi F is 50. L2 is 0.02. You will get XL2 value. Similarly, XC is what? 1 by 2 pi FC. 2 pi into F50 into C is 200 microfarad. Isn't it? 200 microfarad. See here, 200 microfarad. So 200 into 10 power minus 6. Simplified, you will get XC. So determine impedances. So I will write Z1, Z2, Z3 so that it will be easy for you. So impedance of this branch is Z1. Impedance of this branch is Z2. Impedance of this branch is Z3. Three branches are there, Z1, Z2 and Z3. Okay. So determine, just write down the impedance values. So you have determined the XL and XC values. Write down the impedance values, Z1, Z2 and Z3. Okay. So these are the impedances for each branch. Now you know the impedance of each branch. You can determine the total impedance of the given circuit. So Z is equal to what? Z1 plus Z is equal to total impedance Z1 plus Z2, Z3. How are they? Z1 plus Z2 and Z3 are parallel to each other, isn't it? Z2 is parallel to Z3. Z2 is parallel to Z3. Okay, so just simplify them. You will get the total impedance. You know total impedance, you know the source voltage, you can determine what? Total current. So this is my total current. Okay. Now what is the power consumed in the given circuit? Consumed power means what? Active power. Consumed means active power. Formula is P is equal to VA cos phi. We know V value, we know I value, we know phi is the phase angle between voltage and current. Phase angle of this you can see you have got some 30.75. So just substitute, you will get the real power consumed. What about the power factor? Cos phi. So you know phi value, just substitute in cos phi and you will get power factor. Okay, so that's it. I will just create the Google form. You can fill the Google form. as you fill the Google form, you can mention in the chat box and link. I will take another session after 2 p.m. today.